able to see very well.
All right, so you got on the video. Are you happy now? All right.
Wait, I want to be on the video.
So, okay, you are.
Yeah.
All right, so I'm just going to go through the animations quickly here. I actually haven't tested all these out, which is a little dangerous since I'm making a video on it, but the first one worked, so that's good. All right, so you're supposed to go through the animation. It says it's going to show a system at equilibrium. So again, I'm just doing this in case these aren't working on your computer, so then you'll be able to at least see it. So here we go. We're adding solid CoCl2 to water. The solid CoCl2 dissolves and turns pink, okay? So you've got the CoCl2 and the reaction that's happening here. It's actually forming a complex with water, okay? So it's kind of a two-step process where in the first step, the cobalt chloride breaks apart in the water, it ionizes, and then once you have the CO2 plus ions, it's going to form a complex with 6 water molecules to form COH2O6, 2 plus. So that sort of, if you remember the coordination complex rules we talked about earlier in the year, that breaks the rules a little bit in the sense that it doesn't break the rules, but it's kind of an exception. You would expect this to be a CO3 plus because it's forming a complex of 6 ligands, and usually the ligands are twice the charge, but here it's actually forming with 6 H2Os. So that can happen. All right, so let's keep going on the simulation here. So now we've got the cobalt with the H2O, and that's actually a pink, it turns a pink color when it complexes with the water. So the circle represents a small volume of the solution at the particulate level of matter. So it's showing what's going on at the particle level. So you've got your CO connected to the 6 H2O molecules. And there's a lot of water surrounding it, okay? So obviously there's, these cobalts have a lot of water molecules that they can complex with, okay? So there's an overabundance of water there. Pink dot's going to be used to represent one complex ion, it says. So then, again, we've got a bunch of those, and some Cl minus in the solution, okay? But then let's say that we add hydrochloric acid to the solution. Okay, so now the first question on the this animation, it says, how does adding Cl minus ions to the cobalt complex change the reaction conditions? Okay, so now we put the HCl in there. The H plus are just spectator ions, so we're going to leave those out just so you can see the chloride ions a little bit better. All right, so you add the chloride ions into it. And it turns out this will form a separate complex with cobalt, okay? So the complex that can form here is cobalt with 4 chlorines, 4 chloride ions, to form COCl4 2 minus, okay? And that is actually blue in solution. So then what you end up with is an equilibrium that looks like the one at the very bottom here. You've got your cobalt H2O complex on one side, and you've got your cobalt chloride complex on the other side. And you can push this reaction one direction or another, okay? If you push it to the left towards the cobalt with the water, then you're going to get a pink solution, and then if you push it to the right, so you have more of the cobalt chloride complex, then you're going to end up with a bluer solution. All right? So there are certain things that we can do to shift the equilibrium. So the answer to the first question, I guess, how does adding the Cl minus ions to the cobalt complex change the reaction conditions? It's going to turn it blue because it's making more of the cobalt chloride complex. Okay? So they begin to actually replace water molecules. Okay, you've got that Cl minus in there. And then once there's enough of it, it can start to replace those water molecules. Count the number of Cl minus ions and count the number of pink dots. You don't necessarily have to do that. Okay, so now it's changing to a more purple-ish type color because you're getting the blue in there. Okay, it says there are apparently 8 fewer chloride ions. There are apparently 12 new water molecules. Okay, and the reason for that, again, is that the chloride ions are complexing with the cobalt now instead of the water. So you add more HCl. Okay, now you're getting more of those cobalt chloride complexes forming, and it starts to turn bluer and bluer. Okay. So now watch what's happening. Okay. So now we've developed this equilibrium here. Okay. And in the equilibrium, at any given moment, you've got more of the blue of the cobalt chloride in this particular setup than you have of the cobalt with the water complex. Okay. So you're going to overall, you're going to see a bluer solution in here, even though it's constantly changing back and forth between the two, because there's more of the cobalt chloride than there is of the cobalt in the water. Okay. All right. How does adding water to the blue complex change the reaction conditions? So now we can actually add water to this thing, I think. So we add water. Okay, so now the system is no longer in equilibrium when we add the water. And that's actually going to cause it to change back pink, because now there's more water molecules available to complex with cobalt, so then it changes to a pinker color. So now we've got more of the pink than we do of the blue. So that's kind of how that works. Why do these changes in conditions cause reactions to occur? Provide equations to illustrate how these changes in reaction conditions alter the position of the equilibrium. Okay, so basically what you would need to do here, the main equation you need is the one on the bottom here. And then you can just talk about how, adding more water is going to, water is a product over here. Okay, so you're basically adding a product at that point. That's going to push the equilibrium back towards the left to make more of this cobalt water complex. And then if you add more of the chloride ions, more of the HCl, then you're adding more of a reactant. You're pushing it towards the products. Okay. All right. So I think that's pretty much all we need to talk about for that one. Animation number 2. Let me get this one typed in real quick. I should have had all these pulled up. Looks like a lot of this is typed in already. I should have just, okay. Well, for next time. Into O4 equals 8. Without, oh, I typed in something wrong, I think. Hey, this is where I pause the video and then find the website. Alright, so here's the second animation, and this one's an equilibrium between NO2 and N2O4, which you've seen a representation of this several times in your book already, okay? So the first question here says, each time the animation stops, count the number of NO2 and N2O4 molecules present. What do you observe? Okay, so it says press continue to advance the animation. So it's saying count the number of NO2 and N2O4 molecules. 1, 2, 3, 4. 4 of the N2O4. 12, it looks like, of the NO2. Okay, so we can continue. It says, please watch these molecules for a moment. Okay, so these molecules are about to hit one another, and I'll bet you can guess what's going to happen. They actually react here, okay? And then it says, please watch these molecules for a moment. Okay, so then it looks like we had some additional reactions occurring here. Okay, so basically you can see what's happening. You've got them basically breaking apart and reforming and breaking apart and reforming. Okay, so that's an equilibrium system, right? It says each time the animation stops, count the number of NO2 and N2O4 molecules present. What do you observe? After watching the animation panels that include the yellow arrows, describe what is happening simultaneously to keep the number of each type of molecule constant, and explain how this animation illustrates the dynamic nature of equilibrium. So I don't want this video to get too long, so that makes sense, right? Can you answer those questions? Okay. So then let me pause this again, and we'll go to the last animation here. Okay, last animation here. It says the first instruction on the question says, when the animation stops, count the number of Br2 liquid and Br2 gas molecules present, and what do you observe? So this one is actually showing a liquid-vapor equilibrium, so it's not actually even considered a chemical reaction, it's just a physical process. The rectangle represents a volume of 1.0 times 10 to the negative 21st liters, so a very, very small area, okay? So count the number of Br2 molecules in the gas phase and in the liquid phase. So you've got did I miss something? What's the key here? Why are they different colors? I'm a little confused here. Following animation will show representation of this in liquid vapor. Let's continue here. See what happens. Count the number of Br2 molecules in the gas phase and the liquid phase. For every Br2 molecule that enters the gas phase, how many Br2 molecules enter the liquid phase? Okay. So, yeah, I guess, I don't know why they're different colors like that, but I guess you just count the ones that are in each of the different phases. So, you've got, it looks like 3 right now in the gas phase, 6 in the liquid phase. Okay, and so then you can actually look at what we started with. We started with 3 in the gas phase and 6 in the liquid phase. Okay, and then you play through this whole thing. And basically, I mean, again, all they're trying to show you here is that the nature of equilibrium is dynamic. Okay, it's always moving, but you're always going to end up with relatively the same amount of reactants and products or liquid and gas molecules or whatever it is that you're looking at in your equilibrium. So the second question is, the chemical equilibrium or physical equilibrium? I think I already answered that question. And how would you design an experiment to determine if this animation is an accurate representation of what actually occurs? So you have to think basically about how is it that you could prove, or, you know, demonstrate, maybe not prove necessarily, but demonstrate the likelihood that there are gas molecules that are entering the liquid phase, and there are liquid molecules that are entering the gas phase at any given time. Okay? So I'll let you think about that one. And I think that's pretty much it. Those are way more basic than I thought they were going to be. Probably didn't need to go over that, but I guess this way at least you can see the animations in case you can't get through them on your computer. So, so for tomorrow, you basically just need to make sure that you have those pre-lab questions answered and have the background section done. And then we'll just play around a little bit tomorrow, and then you can write your procedure on Tuesday night. Okay? All right. We'll see you in class.